In these notes, we're going to be reviewing exponential functions. What is the difference between linear and exponential functions? Linear functions have a set of coordinates that have a constant rate of change. We also call this the slope. Exponential functions, on the other hand, have a set of coordinates that have a constant multiplier. So if we break down the parts of an exponential function, which we see below, y equals a times b to the x. A is our initial value, just like it is the b in our linear equation. A is the same as b. And then b is our multiplier, which is sort of like our m, our slope. But instead of it adding or subtracting, now we're thinking about multiplication or division. Y is typically a total, and x is typically time. So examples, tables, graphs, and functions. There are two types of linear functions, those that increase and those that decrease. The same is for exponential functions, but instead we say growth, which is the same as increase, and decay. This is typically because we use exponential functions to describe scientific experiments. So in our first example, we're going to be doubling. So whenever b, which is our multiplier, is greater than 0, so this says b greater than 0. That means that we have a growth function. So if we're multiplying by 2, because that's what doubling means, 1 times 2 is 2, 2 times 2 is 4, and 4 times 2 is 8. If we were to graph this, 0, 1, again, that is our initial value. Just like it is for linear function, the initial value is where our line crosses the y-axis. Our next point is 1, 2. We then have 2, 4, and 3, 8. This is going to give us a curved line. We know that it's growth because we read a graph from left to right. And if I follow my line with my marker from left to right, I notice that it goes up. So if we wanted to write this as a function, just like with y equals mx plus b, we always leave y and x blank, or we leave them as they are. Same for exponential functions. Y equals a, which is our initial value. Our initial value on our graph is 1. We can also see it from the table here. So 1. And our multiplier, which is b, is 2. So I'm going to put that in parentheses and give it to the x power. So if I plugged in these x values into this function, I should get the same output. Let's see if that's true. So if we plugged in 0, 2 to the 0 is 1, so y equals 1, which is true. If I plugged in 1, 2 to the 1 is 2, 2 times 1 is 2, and that is true. When x equals 1, y equals 2. When I plug in 2, 1 times 2 to the 2, well, 2 squared is 4. 4 times 1 is 4. When x equals 2, y equals 4. And that'll continue being true throughout the function. So you can use this to find any value, including those that go past our graph or past the numbers in our table. And it'll tell you what the y value is. So you can use this to predict or tell the future. In our second example, our multiplier is a fraction. And our fraction happens to be 1/2, which is less than 0. So when our b, or our multiplier, is less than 0, that means we're going to have a function that decays. Decay is going to be the opposite of what this looks like, where it's actually decreasing. So if we were to cut our input or output in half, 1 times 1/2 is 1/2. 1/2 times 1/2 is 1/4. 1/4 times 1/2 is 1/8. So that means if we were to graph this, our initial value again is 1, but our graph is going down. 1 is going to be 1/2, so I'll put a point that's halfway between 0 and 1. When I go over to 2, 2 is 1/4, so I'll put that point a little bit lower, and 3 is 1/8. So you'll notice that our graph is decreasing because it is decaying. This line, however, will never, ever, ever touch the x-axis. 1/8, if we kept going, if we cut that in half, it would be 1/16. 1/16 times 1/2 is 1/32. 1/32 times 1/2 is 1/64. You will never, ever, ever be able to get 0 if you continue multiplying by 1/2. So this line will never, ever, ever have to touch the x-axis. It'll just get super, super close to it. So if we wrote a function that represented this, again, y equals our initial value, or our a, is 1. And our multiplier, which is b, is 1/2, because that is what we continued multiplying by, to the x power. If we plugged in our values for the x's, we should be able to get the y's using this function. So y equals 1 times 1/2 to the 0. Well, anything to the 0 is 1. So when x is 0, y is 1. That is true. 1 times 1/2 to the 1 power. 1/2 to the 1 power is just 1/2. 1/2 times 1 is still 1/2. So when x equals 1, y equals 1/2, which is true. Y equals 1 times 1/2 to the 2nd power. Well, we learned in exponents that we would give this to both the bottom and the top, or you could think of expanding it. 1 times 1/2 times 1/2 is still going to give us 1/4. 1 times 1 is 1, 2 times 2 is 4. So when when x equals 2, y equals 1/4. So again, you can use this this equation to predict anything forwards on the x-axis as well as anything prior, so any negative values. And we will talk about that in just a moment.